Good afternoon, everyone.
Good afternoon, sir.
Good afternoon, sir.
Today is lecture number 6 of this advanced concepts in steel technology. And today's topic is strengthening mechanism in polycrystalline materials. So this is one of the important topic we have in this subject. So this is materials we use and see are single crystal or polycrystals. So this is a question from my side. So what is your answer for this? So basically what the materials we use in day-to-day life and we basically see are basically polycrystalline. Basically the metal we use, the steel we are using, right? The copper, aluminiums, any metallic materials we are using, basically they are polycrystalline. Poly means many and crystalline means many number of grains or crystals are there, right? Hardly we have single crystal materials in day-to-day life. But one example I can give you where we use a single crystal basically in case of turbine blades. And the reason of that can be explained later. Okay, now the question is the reason behind the weakening of crystalline materials, metals, alloys. So the reason behind the weakening of the crystalline material is the presence of linear defects, right? So basically, you understand, if we have a single crystal, a single grain, right? It is a perfect crystal, we can say. Perfect means there is a perfect ordering of atoms throughout the materials is there, starting from the center of the grain to the, or starting from the center or core part of the material to the end of the surface. We have a perfect order arrangement of atoms over there. There is no deviation in the ordering, right? And you can understand that is free of defects. A single crystal is basically free of defects. There is no grain boundary. You can say there is no dislocations, right? So it is a defect-free crystals. So it has very high strength, basically. The strength is nearly equal to the gigapascal level, right? That is equal to the theoretical strength, as we called, is nearly equal to the theoretical cohesive strength, we can say. But the moment we have polycrystalline materials, that means the material is having lot of grains, right? So lot of grain boundaries are there, right? So that is one of the defect, surface defect, we can say. And we can have dislocations in the material. And you understand the dislocations generates during solidification, basically, or during this some working. Dislocation generates. So these dislocations are the main cause of weakening of the crystalline materials. You can say the presence of these linear defects, those are dislocations, are the main cause of weakening. So material get weakened. So weakens means the strength, the yield strength, the tensile strength will go down. Basically, yield strength will go down to a large extent if we have dislocations in our materials, linear defects. Now we can see dislocations make the crystal weak because due to motion or propagation of dislocation on application of load, high temperature and load, right? You understand that means due to this motion of dislocations or propagation of dislocation in the material, we have slip, or we can have plastic deformation in a crystalline materials. So that means you understand, if our material, suppose our steels, because the subject is concerned with the steels. So if we have a steel, that means we have a polycrystalline steels, and dislocations are present, and this dislocation is propagating from one position to another. So that means if dislocation is propagating, means the slip is happening or the plastic deformation is happening. That means the material is weaker one. So here I have written, or in other words, during plastic deformation, lot of dislocation propagates in slip system, right? So that means the dislocation is gliding, or you can say sliding, on the slip planes and slip directions. And if you remember, what is a slip plane? Slip plane is a close packed plane where the density of atom is more. Sorry, yes, the atomic density is more over there, right? And slip direction is same. In that direction, particular direction, number of atoms are more, or atoms are closely packed in that direction particularly. So if you remember, in case of FCC materials, the slip planes are basically 1 1 1 and slip direction is 1 1 0, whereas it's just opposite to that of BCC materials. In case of BCC, the slip planes are 1 1 0 and direction is 1 1 1. Fine. You can justify like this. In case of BCC materials, the slip direction is along the diagonal, right? Because the body centered atom is present. That is the slip direction. The body diagonal direction is the slip direction. And you understand why this sleep why this dislocation will propagate or move along a sleep plane and sleep direction, because a less force will be required to move the dislocations. Dislocation can be moved just by applying a very low force or stress, you can say. Easy movement will be there. And I have written, once the material deformed plastically, it is weak. That's why resistance to plastic deformation can be called as strength of a material. So basically, in a general way, you can justify the strength by saying resistance to plastic deformation or resistance to movement of these dislocations, right? So similarly, I can say yield strength, stress required to move the dislocation. This is a simple way to define yield strength. Stress required to move the dislocation. If stress required to move the dislocation is high, then yield strength is high. If stress required to move the dislocation is low, the yield strength is low, right? And here I have written, if strength increases, ductility in the material decreases. Or if, I can say, if the ductility increases, strength will decreases. Here I have written, and if the dislocation motion is easy in the material, then we can call its ductility. It's a high ductility. So you understand what is the conclusion of this part. The conclusion of this part is, if the dislocation is propagating easily just by applying a very low load on the material, that means it has high ductility or it is weaker, right? But if you are applying more load and the dislocation is not moving easily, that means the material has high strength. So the conclusion of this topic is written over here. The principle of strengthening of crystalline materials. What is the principle behind this then? So to increase the strength of a crystalline materials, we have to impede or restrict the dislocation propagation of motion. So the best way, or the principle behind the strengthening of materials, how we can increase the strength of the materials, just by restricting the motion of dislocation, right? Or impede the dislocation motion, or to hinder the dislocation motion, right? Or reduce the ability of this linear defects, dislocation through the metal. Now we'll discuss ways to restrict or impede the dislocation motion in polycrystalline materials, or what are the different mechanisms by which we can harden or strengthen a materials. So these are the ways, or sorry, these are the mechanisms. One is the grain refinement, one is the cold working sometimes called strain hardening, dislocation strengthening, solid solution strengthening, dispersion strengthening, precipitation strengthening, transformation strengthening. So these are the various mechanisms by which you can increase the strength of material. And you have to remember, these strengthening mechanisms can be applied individually or in combination, right? You can, if you want to increase the strength of the steel, so you can apply various mechanisms together, or you can apply a single mechanism to increase the strength. That is depending upon the application part where you are using the materials, because obviously the cost may increase during the processing. Now we'll discuss the strengthening mechanism and obstacles to dislocations. Obviously, as I told, if you increase the obstacles to the dislocation motion, you can increase the strength of the materials, right? So in this part, will these are the strengthening mechanisms, and here, what are the obstacles to the dislocation motion? So grain size refinement. Grain size refinement means we are reducing the grain size. That means coarser grain become finer grain, right? So here obstacles is the number of grain boundaries, or you can say grain boundaries. So so here we are increasing the grain boundaries numbers. Just by increasing the grain boundaries number, we can increase the strength. So in cold working or strain hardening or work hardening or dislocation hardening, all are same thing. So here the dislocations are the main obstacles. So if the number of dislocation will be more and more, there is a hindrance to the dislocation motion will be there, right? So more number of dislocation are the obstacles to the dislocation motion, or dislocation forest, you can say, forest of dislocations. Similarly, solid solutions. So solid solution strengthening. Solid solution strengthening, the main obstacles is the strain field around the solute atoms in parent lattice, right? Because you understand, when you are adding solute atoms or the alloying elements into the parent lattice, what happens? The size may be differ. Already we have studied that in thermodynamics, if you remember. There is a strain in the lattice will occur. That strain field actually hinder the dislocation motion, right? Then precipitation strengthening. Precipitation strengthening, here the obstacle to dislocation motion is the precipitates. Precipitates are basically second phase particles. Hard particles like carbides, nitrides, carbonitrides. These are formed due to addition of alloying elements. For example, niobium carbides, vanadium carbides, those are second phase particles in the steels. They hinder the motion of dislocation. Then dispersion strengthening. Here dispersion strengthening, here insoluble hard particles. Here basically what happens, intentionally we add some hard particles like oxides, oxides, oxide particles, which are insoluble. Basically they will not become soluble in the matrix phase. For example, yttrium oxides or titanium dioxide present in the steels. Steel means, suppose it is ferrite matrix and you are having TiO2 particles and yttrium particles, yttrium oxides. They will, they are basically insoluble and hard particles. Fine, they will restrict the motion of dislocation. Then transformation strengthening. Transformation strengthening, you understand, the austenite can be transformed into martensite or austenite can be transformed into vanite, which are basically non-equilibrium products, and that leads to lot of strain in the materials. So again, this is actually due to strain in the materials which restrict the motion of dislocation due to formation of these non-equilibrium products. Martensite is a non-equilibrium product and vanite is a non-equilibrium product. Non-equilibrium microstructure. Why? Because they form due to very fast rate of cooling. That's why they are non-equilibrium microstructures. Okay, so and this topic now, the topic here is, as I told, the first mechanism, which is grain size refinement. We'll discuss that. You can see this is a polycrystalline materials. You can have, this is 1, 2, 3, 4, 5, 6, 7, 7 number of grains, or yes, 7 number of grains are here. Sorry, 8 number of grains. This is another grain. So we have many grains like this. This is just a part of the microstructure. And what is the observation? Can anybody tell me what is the observation you are looking at here? Suppose these lines, you can call, these are the these lines are what? These are the planes, huh? These are the slip planes, for example. Fine. These lines are slip planes. So what is the observation? Can anybody tell me? As I told, the hint is these lines The darker lines are the slip planes. So what is the observation here? We have a polycrystalline material here.
Due to many grain boundaries there, the slip lanes gets restricted.
No. I am not asking that. I am saying these are many grains present, and these are the slip planes. So what is the observation you are getting? Compare this grain with this grain. Compare this grain with this grain. Compare this grain with this grain. So what is the observation you are getting?
So somewhere the dislocation density is more in here.
Dislocation density. I am not able to see any dislocation here.
That
I'm saying compare this grain with other grains, or compare this grain with other grains, and carefully look at this image. And hint is I am showing you these are slip lanes. Just look at the slip lanes in different grains. Just look at the slip planes in different grains and tell me.
the orientation of slip lanes are changing.
Yes, very good. The orientations is different in different grains. So slip planes are differently oriented. You understand how a grain boundary forms, right? If you remember how a grain boundary forms, when you are solidifying a metal or an alloy, nucleation will start from different regions, and this nuclei will grow and meet with one another. The moment they meet, that forms a grain boundaries, right? Because you understand each grains have different what unit cells, huh? And unit cells in a single crystal is having a order orientation. They are oriented in a particular directions. But if you look into different grains, then different grain have different unit cells orientation in different directions. So that is why you can see in this grain the crystallographic slip planes are in this direction, like this. But if you move to this grain, this is like this. If you move to this grain, this is like this. If you move to this grain, this is like this, right? So in different grains, we have different crystallographic orientation of the slip planes, right? So that's why we have a grain boundaries here. We have a grain boundaries here. We have a grain boundaries here, which is not clearly visible, this one. Because you can see this is the slip planes, but here the slip planes are here like this. Okay. And just look at this image again. This is one grain, this is another grain. You can see these are the, what is this pink part? What is the pink part here? What is the pink part here?
Dislocation.
Dislocations, edge dislocation. You can see the dislocation is moving in this direction towards this. But the dislocation is easily moving in this direction, or dislocation is propagating in this direction. But the moment it will face a grain boundary, it will become stop. It cannot move. Why? Because the orientation in this boundary, in this grain is like this. The orientation in this grain is like this. So due to different orientation in this, or due to different orientation of the slip plane in this adjacent grain, this dislocation cannot move. It will get restricted here. It will stop over there. So you understand from this. So grain boundary is an obstacle to the dislocation motion. That is the conclusion here. You can just look at this one. This is a single crystal, and this is a polycrystal. Many grains are here. Many crystals are here. But this is a single crystal. This is a single grain. And this is a dislocation. And you can see these are the orientation of the slip planes. So see, just dislocation is easily gliding. Easily gliding. It will glide and glide. There is no issue. But here what happens, many grains are here. So many grain boundaries are here, right? So you can see, suppose I am comparing these two grains. Here the orientation of the slip plane is like this in this grain. But in adjacent grain, the orientation of slip plane is like this. So there is a difference in orientation of the slip plane from one grain to another, right? So what happens? This location will easily glide in this plane in this grain, but the moment it will reach the grain boundary, the orientation is different. So it will stop. So conclusion here from this image is grain boundary is an obstacle to the motion of dislocation. So the dislocation cannot cross this grain boundary, right? So what happens if dislocation cannot cross this grain boundary? Further plastic deformation will be restricted. There will be no plastic deformation, right? But we want plastic deformation to happen. So what happens? We have to apply more stress. The moment the stress will be more and more, obviously that means the strength is more in that materials, right? Then more stress can be introduce more dislocation in the materials in this grain, and they will start propagating again, right? So this is the conclusion here. So what is the conclusion? You can see this. Just imagine, just look at this one. This is a coarser grain material, and this is a very fine grain material here. Coarser grain material means you can see number of grains are less, number of grains are more here. Since the number of grains are less, we have less number of grain boundaries. Here the number of grains are more, we have more number of grain boundaries, right? Material is same. So what happens? The conclusion I have written here. Finer grains, more number of grain boundaries. More number of grain boundaries, more obstacles to the dislocation motion. So what happens? More stress is required to move the dislocation. So due to which the strength in the material increases. And I have also written here, because of different orientation of adjacent grain in a polycrystalline material, the dislocation cannot move to the next grain from the grain in which it is moving. So grain boundary become the obstacles for the dislocations. And to produce new dislocation in adjacent grain, more stress is required. So this is the conclusion of this topic. I think everybody have understood. Now, how this can be justified? You can see the grain size is decreasing, the strength is increasing, right? And this can be justified with the help of Hall-Page relationship. Hall-Page relationship is what? It is a relationship I have written here actually. Just look at this one. Hall-Page relationship. There's a relationship between yield strength of the material with the grain diameter or grain size, right? The Hall-Page relationship give you relationship between the grain size or the diameter of the grain with the yield strength. Whether the yield strength will increase or decrease, that will be affected by the grain diameter. Here you can see the relationship sigma y is equal to sigma naught plus k d to the power minus half. Or you can write like this, sigma y is equal to sigma naught plus k divided by root over of square root of d, right? In this way you can write, either of this way you can write it down. So here what happens, sigma y is actually yield strength of the material, sigma naught is a constant, k is a constant, and this d is the diameter of the grain, or grain diameter. So if I would like to plot sigma y versus d to the power minus half or 1 by root over of d here, like this. This is y, in y-axis we have sigma y, which is the yield strength, versus 1 by square root of d or d to the power minus half, anything you can write. So this plot is, you can see, it is a straight line, it is a linear line. That means what happens? With decreasing in the grain size in this direction, the yield strength is increasing. These points are actually data. When the grain size of this much, the yield strength is this much. When the grain size of very finer size, this one, the yield strength is this one. When the grain size is this much, the yield strength is this much. These are the data points. So you can see with decreasing in the grain size, the yield strength is increasing. There's a linear relationship, right? And what is the intercept? You can see the intercept is the sigma naught, this one. This one is the intercept, right? What is that? Basically, the intercept is sigma naught, which is nothing but this one, the yield stress for an infinite large grain size, or for a single crystal. This is the, if you have a single crystal, then your yield strength is equal to sigma naught, right? And slope is what? This is the slope, which is nothing but the K, right? So in this relationship, K is the slope and sigma naught is the intercept, which is nothing but the theoretical strength or strength of a single crystal, basically. So here I have also shown you the relationship. You can see I have taken an example, 70% copper, 30% zinc materials. In this way, this is a material, polycrystalline materials. And you can see this is the grain size axis and this is the yield strength axis. The grain size axis and this yield strength. When the grain size is becoming more finer and more finer, you can see the yield strength is increasing. And this slope is the K. And the intercept is this point. Right? You can see the grain size is decreasing, the yield strength is increasing. Now the question is how to measure the grain size. So there is a way called linear intercept method. Linear means straight. Intercept means that particular line will intersect the grain boundaries. So linear intercept methods. It is also called mean intercept size. You can see we have a microstructure here with a particular magnification of n. These are polycrystalline materials. Many grains are here, right? With magnification m. Magnification is m. So what this method is saying, you draw a line, you draw a straight line of a given length. Suppose this is a straight line of a given length, L. And these are the intercepts, 1, 2, 3, 4, like this. Suppose n number of intercepts are there. That means this straight line is intersecting n number of grains boundaries. N number of grain boundaries is intersected by this straight line here. Then count the number of intersections. Suppose your intersection is 4, but you can call n. So what is the real length of this line? This is not the real length. Why? Because this image has taken at a magnification of m. We have blown off the image. So that's why what is the real length? Real length will be the L divided by m. Fine. Where L is the length and m is the magnification here. So that will give you the original length. Now, where if n is the intercepts, number of intercepts, how many grain boundaries are intercepted? That is n. Then so we can define the grain diameter as L divided by m into n. So this will give you the size of the grain. But this is not the original diameter. You have to take the mean size. So you have to draw many lines like this. After drawing many lines, you have to find out the d, and finally you have to take the mean of that. So this will give you the grain size. So this is one of the way, linear intercept method to find out the grain size. But nowadays we have softwares which will easily give you the grain size easily without doing this manual method. Now we'll discuss about the favorable condition or situation for selection of a suitable grain size. Whether we have to choose a small grain size or we have to choose a coarse grain size, polycrystalline material for the specific applications. See, the point is what? Basically, it is not always true that when we choose a very fine grain materials, it is beneficial for us. It is not always true. Sometimes what happens, sometimes a single crystal is very important with a very large grain size. That means single crystal with a very weak grain size. Or we can have a coarser grain which is beneficial sometimes. So basically it depends upon the application area where you are putting your steel into applications. Suppose you are making a turbine blade. You can see area of application is turbine blade. So you understand that turbine blade means here a very high temperature will be existing, right? Prevailing. And you are having a high pressure also. So in that condition, what happens? I have written controlling condition prevailing is high temperature and high pressure. Temperature above 500 degrees centigrade, for example. The steam or the gas which is bombarded on the turbine blade is above 500 degrees centigrade. You can imagine very high temperature. So you understand when the temperature is very high, what happens? What happens basically? Diffusion starts. Diffusion is more, right? At high temperature, the diffusion is more, and when the diffusion is more, what happens? The growth will be there, right? So what happens? The turbine blade will grow in a particular orientations, and it may strike the casing. Casing means the outer body. Finally, it will break. So this is one of the major issue. You understood? So when you are using a steel for high temperature applications, in that condition, what happens? The grain growth may happen, and the blade may grow into a bigger size, and it will strike the casing. Fine, it will break. And another issue is what? Due to diffusion mechanism, creep failure occurs basically. So we have to minimize the creep, right? So that's why suitable grain size is coarser or finer. Sorry, coarser or single grain material we have to use. Why this happens actually? You understand, if we have more number of grains, and grain boundaries is more obviously, and grain boundary is an easy diffusion path, right? If you carefully look at the, if you magnify a grain boundary, you can able to see dislocations are actually present over there. Many dislocations are present, one below another or one above another, and there is a tunnel shape way will be present. And the tunnel shape way is actually a easy diffusion path. Maybe I'll show you in the next class or next class how it looks like basically, right? So grain boundaries is a easy diffusion path. That means along the grain boundaries, the atoms can easily diffuse out, or the vacancy movement will be easy, or the atomic movement will be easy. They will diffuse easily. So if you understand, if diffusion will be easier, what happens? The grain growth will be there, and the turbine blade will grow in a particular orientations, and will strike the casing. Or it may happen, it will make the creep failure easier, or the creep resistance will be decreased, right? So that happens if we have a more number of grain boundaries. More number of grain boundaries are present in a finer grain materials, right? So that is why the solution is you have to use either coarser grain or single grain material. The best solution is using single grain materials basically. And another point is, suppose the area of application where the application area is automobiles, bodies, construction materials, where the temperature is very low, relatively low, that is below 500 degrees centigrade, or basically room temperature application. So here diffusion is insignificant, right? There will be no diffusion because temperature is not high. It is unimportant here, right? So in that condition, you have to use fine grain materials. Fine grain materials. Grain size should be very low, right? So I think you understood the conclusion of this one. So grain boundaries are easy diffusion path, blade length increases and hit the engine casing, right? And fine grain helps in creep failure. Right? So that this is due to this reason we are using coarser grain material or single grain materials. But if your area of application is very low temperature, we have to use fine grain materials because there will be no diffusion actually. This is the main part here. Then this, just read it. Requirement of modern turbine blades in modern engines. Suppose nowadays our requirement is what? We have to go to a very high temperature in case of this one, 1000 degrees centigrade, or temperature above 600, 700 like that. And the turbine blade can work up to 10,000 hours. It will not fail up to 10,000 hours. So if this is a requirement, if temperature is very high and turbine blade has to work for 10,000 hours, so what happens? We have to use a single crystal turbine blades or coarser grain materials basically. So the solution is what? Solution is to eliminate more number of grain boundaries. You understand? If the grain boundary will be eliminated, that means the grain will become coarser or we can produce a single crystal maybe. I think this part is clear. Next, move to problem associated with the increasing the strength in the materials. So basically what happens, as I have shown you here, this one, when the strength increases, the ductility decreases. Or in other words, I can say when the strength in the material increases, the toughness of the material decreases. Because you understand, toughness is the combination of these two, strength and ductility. That means the material should have good strength as well as good ductility. But the problem is what, when the strength increases, the ductility decreases. So it decreases the toughness of the materials. So here I have written, toughness reduces with increasing the strength. So what is the solution? The best solution is the grain refinement. So grain refinement is one of the important strengthening mechanism where we are increasing the strength as well as we are increasing the toughness of the materials. But if you apply other mechanisms, if you look, you will see that the problem is what, that with increasing in the strength, the toughness will decrease. But in the grain refinement method, the strength will increase and toughness will also increase. And another one is the Bainitic Transformation. Bainite is one of the interesting phase, which is a non-equilibrium product because it is formed by non-equilibrium cooling, very fast rate of cooling sometimes. It provides you good strength and good toughness, right? But if you compare other strengthening mechanism like this, this one, and this one also, here strength increases but toughness decreases. But this one will increase the strength as well as increase the toughness of the material. Okay, I'll end the topic here. If you have any doubt, you can ask me right here.